We continue with our discussion on anisotropic media. Do you have any questions? Okay, so we started discussing anisotropic media in the last class. So let me recall, we had written this equation d is equal to epsilon e, where epsilon is now no more a scalar, it is a tensor. So this will essentially imply that in general d and e are not parallel to each other. These are the two Maxwell's equations we will use to study propagation of waves, and what we try to look for is plane wave solutions of the type given by E is equal to E0 exponential I k dot r minus omega t. Now, as I was mentioning in the last class, if I assume E naught vector to be independent of position, it implies that we are looking for solutions where the state of polarization represented by this E0 vector is maintained as the wave propagates. We do not know what polarization states will lead us to the solution. So, E0 vector is still an unknown. What is the direction of the E0 vector, whether it contains components which are in phase, out of phase, etc. We still do not know. And the corresponding H vector we wrote as H naught e to the power I k dot r minus omega t, and here the propagation vector k is actually let me correct here. So, there has to be a unit vector here. So, this is omega by c times some refractive index times a unit vector. This refractive index I still do not know, because the medium is characterized by three principal refractive indices nx, ny and nz, or three principal dielectric constants kx, ky, kz. So, how is this n related to these we do not know. So, we substitute this E and H in this equation and also this expression for D, and as I mentioned before, we will assume B is equal to mu naught H, and we land up with this set of equations, two equations. K cross E is omega mu naught H and K cross H is minus omega D. So, we discussed this last time, and we saw that in general, because D and E are not parallel to each other, K and S are not parallel to each other. So, the wavefront direction of propagation is represented by K vector, the energy propagation is directed by the S vector, and they are in general not equal, not the same. So, what you will have is a wavefront like this facing forward, but going at an angle, oblique angle. So, our objective is now to use this set of equations to find out what are the values of refractive indices that the wave will propagate with and with what polarization states. So, we use these two equations. So, let me write these equations again. So, K cross E is equal to omega mu naught H and K cross H is equal to minus omega D. Now, remember, we have written this equation D is equal to epsilon E. So, this equation actually becomes K cross H is equal to minus. So, let me write this as epsilon 0 times a dielectric constant tensor times E vector. The epsilon tensor is actually epsilon 0 times a K tensor. So, in isotropic media, epsilon would be a scalar, K would be a scalar, and K would represent the dielectric constant of the medium. So, this is K cross H is minus omega epsilon into E vector, K into E vector. Okay. Now, let me take this equation and pre-multiply by K cross. So, K cross E is equal to omega mu naught K cross H. I substitute for K cross H from here. So, this becomes minus omega square epsilon 0 mu 0 K times E. I can expand this A cross B cross C. So, I will have k dot E times k minus k dot k, which is k square times E vector is equal to minus omega square by C square into k E. Epsilon 0 mu 0 is 1 by C square, and I have just expanded this k cross E in terms of k dot E dot k into k minus k square E. So, this equation is actually, this contains 3 equations, 3 Cartesian component equations. So, let me write each equation. For example, the x component of this equation becomes kx Ex plus ky Ey plus kz Ez is a bracketed term times kx, that is x component, minus k square times Ex is equal to minus omega square by c square. Now, remember, we are always using principal axis system. So, in the principal axis system, the k tensor is diagonal. So, what will be the x component of k times E? Kx Ex. So, I will have simply kx times Ex. Now, this k vector is omega by c times n times kappa cap. Kappa cap is a unit vector. So, let me substitute for the kx, ky, kz. So, what I will get here is omega by c times n is common in kx, ky and kz. So, I will get and this kx. So, I will get omega square by c square into n square into kappa x Ex plus kappa y Ey plus kappa z Ez minus omega square by c square into n square into Ex is equal to minus omega square by c square kx into Ex. Now, I can cancel this omega square by c square in all the 3 terms, and I can divide by n square the whole equation. Sorry, there is a kappa x here sitting. This kappa x from here is sitting here. So, I divide by n square. So, I will get kappa x Ex plus kappa y Ey plus kappa z Ez into kappa x minus Ex is equal to kx minus kx by n square times Ex. So, let me now write this equation after opening up the bracket, and what I will get is, so I will have Ex into kappa x square minus 1 plus kx by n square. So, this is kappa x square minus 1 from here and plus kx by n square into Ex plus kappa x kappa y Ey plus kappa x kappa z Ez is equal to 0. So, I have essentially kappa x square Ex minus 1 minus plus kx by n square into Ex, and then I have kappa x kappa y Ey, kappa x kappa z Ez. Now, remember, kappa is a unit vector. So, kappa x square plus kappa y square plus kappa z square is equal to 1. So, kappa x square minus 1 is essentially minus kappa y square minus kappa z square. So, this equation can be written as Ex into kx by n square minus kappa y square minus kappa z square plus kappa x kappa y Ey plus kappa x kappa z Ez is equal to 0. So, that is x component of that vector equation. You can similarly write out the y and z components of this equation, and you can actually use symmetry to write the remaining two equations. So, for example, the second equation you will get is kappa y kappa x Ex plus ky by n square minus kappa x square minus kappa, sorry, this is z square, minus kappa z square into Ey plus kappa y kappa z Ez is equal to 0 and kappa z kappa x Ex plus kappa z kappa y Ey plus kz by n square minus kappa x square minus kappa y square into Ez is equal to 0. I have got a set of three linear equations in Ex, Ey, Ez, in which the unknowns are still n. I do not know the value of n. If I give you a medium, I know kx, ky, kz, the three principal dielectric constants. If I specify the direction of propagation, I know kappa x, kappa y, kappa z. So, I still do not know n, the refractive index, and the corresponding Ex, Ey, Ez values. So, the values of n will be the eigenvalues of this problem, and the electric field vector which has components Ex, Ey, Ez will be the eigenvectors. Now, if you have a set of three linear equations in Ex, Ey, Ez, what is the condition for a non-trivial solution? Determinant of coefficients must be 0. So, if I write out the determinant of these coefficients, you will get an equation in. So, first of all, you notice that it is all n squared, there is no n anywhere. So, you will have n squared terms, 1 by n squared terms, you will have 1 by n 4 terms, 1 by n 6 terms, right. Now, what you can show is when you expand this determinant, you will get a quadratic equation in n square. The sixth power, n to the power 6 coefficient just vanishes. So, you will have a quadratic equation in n square, and so quadratic equation in n square means there will be 4 roots, and you will find that out of these only 2 are real roots of the problem. So, there will be 2 real eigenvalues of this problem, which will actually correspond to the 2 states of polarization of propagation, because light is a transverse electromagnetic wave and you will find 2 independent polarization states. So, let me leave it as a problem for you to show that this opening this determinant will only give me a quadratic equation in n square, and that quadratic equation determinant will give me the solution, and I will have 2 real solutions. Now, instead of doing a general problem, let us look at some example. So, first example I want to see is a wave propagating along z. Please remember this x, y, z is the principal axis system in my crystal, they are not arbitrary. When I say this z is the z direction of the principal axis of the crystal. Okay. So, if I have a wave propagating along z, what is the value of kappa x and kappa y and kappa z? So, what should be kappa x? 0, kappa y 0 and kappa z 1. You have a wave propagating along the z direction. So, the unit vector has 0 components along x and y and has a component along 1 along z direction. So, I substitute this into all the 3 equations. So, let me write down the 3 equations individually. So, I will have Ex into kx by n square minus kappa y square is 0 minus 1.
Kx is 0.
No, kx, please, this is kappa x, kx is the one of the principal dielectric constants of the medium. So, kx, ky, kz, these 3 coefficients sitting here, kx, ky, kz are the 3 principal dielectric constants. This is kappa x, kappa y, kappa z. These are the components of the unit vector. If I am given a medium, I am given kx, ky, kz. Okay, so the second term and third term will be 0 because there is a kappa x, kappa y. So this will be equal to 0, the first equation. Second equation will give me Ey into ky by n square minus 1 is equal to 0, and the third equation will give me kz by n square into Ez will be 0. I substitute these values of kappa x, kappa y, kappa z in the three equations, and the three equations simply reduce to these three equations, simply three simple equations. Now, what is the first conclusion I can draw from here? Ez is 0 because kz is a given principal, is a principal dielectric constant value, n is some refractive index. So, this implies Ez is equal to 0. That is, for a wave propagating along z, the electric field has no component along the z direction. So, I am left with these two equations. So, I can satisfy these two equations under two conditions. The first solution is I can have n square is equal to kx, which will satisfy the first equation, and Ey is equal to 0, which will satisfy the second equation. So, if I choose n square is equal to kx as a solution, the first equation is satisfied, and by choosing Ey is equal to 0, the second equation is satisfied, and of course, Ex must not be equal to 0, because if Ex is also 0, the electric field itself is 0. So, that is the first solution. So, the first solution corresponds to electric field along the x direction, and the corresponding refractive index as seen by this wave is equal to square root of kx. So, if I can draw the axis here, this is z, this is x, this is y. So, the electric field is along x direction, the propagation vector is chosen to be along the z direction. What is the direction of d vector? Along x, because if remember, if the electric field is along one of the principal axis direction, the corresponding d vector is also along the same principal axis direction. So, d is also here. And what about s vector? S vector is parallel to k. This is the direction of h vector here. By using the relationship between the direction of vectors of k, e, d and h, you can calculate s vector, and you see that for this solution, the wave is polarized along the x axis, propagates with the refractive index square root of kx, and propagates along the z direction, and the pointing vector and the propagation vector are parallel to each other. So, this is the wave, this is just like any ordinary isotropic medium with a polarization now along the x direction. So, let me look at the second solution. The second solution is n square is equal to ky, Ex is equal to 0 and Ey not equal to 0. So, the refractive index as seen by this wave will be square root of ky, and if I draw the diagram again, this is z direction, this is x direction, this is the y direction. So, this is k vector, the electric field is along this direction. What is the direction of h vector? Down, right? Yeah, minus x. So, it will be like this. D vector parallel to E vector, and k vector and s vector are parallel again. So, in this case, the electric field points along the y direction and the wave propagates along this z direction, and the velocity of this wave is determined by this refractive index square root of ky. So, if I have a wave propagating along the z direction, if I choose my electric field to be along x direction, it will propagate with the speed of c by square root of kx. If the wave if I choose my electric field to be along the y direction, it will also propagate unchanged, but with a speed c by square root of ky. Please remember, the solutions we have got is a situation where the electric field direction does not change with propagation. So, if you launch a wave along the z direction, but with its electric vector along x direction, it will not change at all, it will propagate x directed oriented completely. If the incident light is y polarized with E vector along the y axis direction, it will also propagate along z unchanged, but with a different speed c by square root of ky. If you choose an arbitrary direction of E vector, so if my x is like this, y like this, z like this, and if my propagation is like this, and if I happen to choose an E vector like this, what would I have to do? I have to break this up into this component and this component. So, if this angle is theta, so I have E cos theta oriented along x cap direction, E sin theta oriented along y cap direction. The E cos theta component will travel with the speed c by square root of kx. The E sin theta component will travel with the speed c by square root of ky, and if kx is not equal to ky, they will develop a phase difference. And when you add two orthogonally linearly polarized light waves with a finite phase difference, you will find a different polarization state. So, as light propagates along the z direction, please remember the electric field, which is the x component, which has E cos theta component, has its s vector also along z. The E sin theta component along y also has its s vector along z. So, the net energy is propagating along z, but with a polarization state which keeps on changing, because the two velocities are in general not equal. So, the state of polarization will change, and these two solutions we have got are the two eigenmodes. Because light is transverse electromagnetic, I will find two orthogonally polarized eigenmode solutions, and these are the two solutions, one along x and one along y for propagation along z direction. Yeah.
In the first case, when you say that the electric field won't change, you were talking about the direction of the electric field. The magnitude is still going to oscillate, right?
Yeah, magnitude okay. The magnitude oscillates as per this equation, e to the power I k dot r minus omega t. What I am trying to say is E0 vector is not going to change at all with z, right. If the E0 vector at the input was x directed, it will always remain x directed. If the E0 vector was y directed, it will always remain y directed. But if the E0 vector is some arbitrary direction now, it will change, because that E0 vector, if I try to substitute into my Maxwell's equations, I will find that it does not remain constant. So, the way I solve it is that any given E0 vector, I break it up into x component and y component. I know how x component propagates with distance, I know how y component propagates with distance, and then I add up at any value of z. It is exactly like Fourier decomposition. It is in terms of two normal modes of propagation. So, I split the problem into the normal modes whose solutions I know, how each normal mode propagates with time. So, if I propagate along x direction, what will be the solutions I will get? It is again by symmetry. If I propagate along x, one will be along y, the other will be along z. The y component electric vector will see a refractive index square root of ky. The z component will see a refractive index square root of kz. So, if I propagate along any of the three principal axis directions, the two eigenmodes are the two other orthogonal principal axis directions, and the corresponding refractive indices seen by the wave are C by the corresponding principal refractive indices. Okay. So, for propagation along the principal axis, the solutions are very simple, and in this case S vector and k vector are always parallel to each other, D vector and E vector are parallel to each other, and the propagation is exactly like an isotropic medium. The only difference is the different components of polarization see different velocities. So, if you launch an arbitrary polarization state into this medium and still propagate along the principal axis, the polarization state will change in general. Okay. Now, let me go to a little more general case.
So this case is only possible when kx equal to ky,
Which case is only possible?
when the electric field has both x and y components.
No, suppose I take electric vector like this. So, E vector is equal to x cap. Let me call it E 0 cos theta plus y cap E 0 sin theta. Okay. Now, what I am saying is this component propagates with a velocity c by square root of k x. This, so, what is the k vector for this? So, k vector for this component, okay. So, let me write like this. Okay. So, at z is equal to 0, the equation is E vector x cap E 0 cos theta plus y cap E 0 sin theta e to the power minus I omega t. Okay, the propagation is along z direction. So, the exponential factor would have been exponential I k z minus omega t, because propagation is along z, k vector is along z, and so k dot r is k z. Okay. So, I have exponential I k z minus omega t at z is equal to 0. This is my crystal is here, this is z axis, this is z is equal to 0. I have launched the wave here with an electric vector like this, oriented at some angle to the x and y direction. Now, what will happen at z? At z, I will write this as, now look at this, when I have x component, the corresponding phase change will be I, what is the value of k? Omega by c square root of k x into z minus omega t. This is the value of k for the x component of electric field. For the y component, the k vector, the magnitude of the k vector is omega by c into the refractive index, which is square root of k y into z minus omega t. I cannot write a k vector for this component, this x cap plus y cap component, right. I have got the solution. I have shown you that if electric vector is along x cap, it is a plane wave propagating with a velocity or with a propagation constant omega by c times square root of k x. If the electric vector is along y cap, it is a plane wave propagating with a propagation constant omega by c square root of k y. So, I have broken up the input electric vector into two components, and then the corresponding phase changes I have written as k times z. Now, if k x is not equal to k y, these two values are different, and so when I add them up at any value of z at the output, for example, the polarization state will not be linear anymore, it will be different.
But if we go back to the two original equations,
Yes,
if both Ex and Ey are non-zero,
you mean where?
the two equations from which we found
These equations?
no, the Ex into Kx by n square.
Okay, yeah.
Now, if both Ex and Ey are non-zero, that would imply that both Kx and Ky are equal and equal to n square, which would mean that their space.
That is not a solution of this problem, because n square cannot have two different values for the same solution. The two eigenvalues are n is equal to square root of kx and n is equal to square root of ky. If n is square root of kx, Ey is non-zero. Sorry, no. If n is square root of kx, Ex is non-zero. If n is square root of ky, Ey is non-zero. These are the two solutions. If you choose any other arbitrary E direction, I would have to write in terms of these eigenmodes, which are Ex and Ey components. Ex component will propagate with its own phase constant, Ey component will propagate with its own phase constant, and they will develop a phase difference. It is like if I have a string, I have the modes of oscillation, the fundamental mode, the first excited mode. If I t is equal to 0, I excite the first and the fundamental and the first harmonic of the string. What will be the shape of the string after some time? You will say the fundamental has changed by so much because the frequency is omega, the first harmonic has a frequency omega dash, and so you will then find the shape of the string corresponding to the fundamental and the first excited after some time and add them up. Exactly similarly I am doing here. So, what I am doing is I am splitting the input electric vector in terms of the eigenmodes, because I know each eigenmode propagates as an independent solution. X component eigenmode will propagate with a certain propagation constant, the y component eigenmode will propagate with a different propagation constant, and they will propagate independently. See, the eigenmodes are all independent, which means if I launch x component electric vector, it will always remain x component electric vector. If I launch y component electric vector, it will always remain y component electric vector. If I launch an arbitrary direction, it would change its orientation, it is not a mode. For example, if the light was polarized at 45 degrees to the xy direction, after some distance you will find it linearly polarized like this. When the phase at this position, the phase difference between this and this was 0. After propagating through a certain distance, there will be a phase difference of pi. When the phase difference becomes pi, the linearly polarized light becomes the other way around. So, this polarization state is not remaining constant, because that is not a mode of the system. Whether you look at this or this component and this component are remaining the same, there is no change in those components. The amplitudes of those two components remain E0 cos theta, E0 sin theta. The only thing that is happening is a change of phase. So, that is the beauty of eigenmode solutions. You break it up, you find the eigensolutions. For any given problem, you break the problem into the eigensolutions and analyze the problem in terms of eigenmodes. Okay, now let me look at a more general case. This is Z, this is X. My propagation direction is some direction psi with respect to Z axis, and in the xz plane. So, what is kappa x? Sin psi. Kappa y. Kappa y is 0 and kappa z is cos psi. Now, let me substitute these into those three. So, I will go back to these equations, substitute these values of kappa x, kappa y, kappa z, and let me write those equations. So, E x times k x by n square minus kappa z square, which is cos square psi. Second term is kappa x, kappa y is 0 plus kappa x, kappa z is sin psi cos psi. E z is equal to 0. The second equation is k y by n square minus kappa x square minus kappa z square is 1 into E y is equal to 0. And the last equation is cos psi sin psi E x plus k z by n square minus sin square psi into E z. So, I have just substituted the values of kappa x, kappa y and kappa z in those three equations, and those three equations simplify to this set of three equations. Now, first thing you notice is these three equations have split into two groups. In one group of equations, the first and the third only contain E x and E z, and the intermediate equation has only E y. So, actually in principle what I need to do is to find the determinant of the coefficients, put it equal to 0, get the solutions, but because of these special cases I can find a solution very quickly just by looking at these equations. For example, one solution can be if n square is equal to k y, this equation gets satisfied. So, I can choose n square is equal to k y, E x is equal to 0, E z is equal to 0 and E y not equal to 0. If I choose n square is equal to k y, this equation is satisfied, and by choosing the electric vectors components E x and E z to be 0, I satisfy the first and the last equation. So, this gives me a refractive index which is square root of k y independent of psi. What is psi? Psi is the angle between the k vector and the z axis. So, whatever psi you choose, one of the solutions will have its electric vector along the y direction, and so if I again draw this is y. So, this is my propagation direction k vector. So, E vector is here. What will be the d vector? If E is along the principal axis, D is also along the same principal axis. So, D is also here, and what will be the S vector direction? Along k. So, this solution has its S vector parallel to k vector. The electric field and the displacement vector are perpendicular to the z plane, and the velocity of this wave is independent of psi. This angle is psi here. Second solution is when I put E y is equal to 0, and then E x and E z have to satisfy this equation. So, let me put E y is equal to, so the second solution is E y is equal to 0, E x not equal to 0 and E z not equal to 0. And how do I find the value of n? From the first and the last equation, the determinant of coefficient must be put equal to 0. So, this gives me k x by n square minus cos square psi into k z by n square minus sin square psi minus sin square psi cos square psi is equal to 0. So, the determinant is essentially this into this minus this into this must be equal to 0, and so I open up the brackets and I get k x k z by n 4 minus 1 by n square into k x sin square psi plus k z cos square psi is equal to 0. The sin square psi cos square psi term cancels off, and because 1 by n square is not 0, I take out 1 by n square from common from both sides, and I will get an equation 1 by n square is equal to so this is cos square psi by k x plus sin square psi by k z. So, in this equation what I have done is, in this equation I have removed 1 by n square, it is not 0, and I have divided by k x k z. So, I will have cos square psi by k x plus sin square psi by k z is equal to 1 by n square. And this has both E x and E z non-zero. So, let me look at the ratio of E x to E z. So, how do I get that? I substitute the solution into one of these equations. So, for example, k x by n square minus cos square psi from here, this implies k x by n square minus cos square psi is equal to k x by k z sin square psi. I just multiply by k x both sides. So, I get k x by n square minus cos square psi is equal to k x by k z sin square psi. So, I substitute for k x by n square minus cos square psi into this equation, and I will get kx by kz sin square psi Ex plus sin psi cos psi Ez is equal to 0. So, if psi is not equal to 0, then I can remove sin psi from here and I will get Ez cos psi by Ex sin psi. I am sorry. Let me write like this. Sorry. Ez kz Ez by kx Ex is equal to minus kz Ez by kx Ex is equal to minus tan psi. Now, what is kz Ez? Please remember x y z is the principal axis system. So, dx is kx Ex, dy is ky Ey and dz is kz Ez. So, this is nothing but dz by dx is equal to minus tan psi. So, what is the meaning of the statement? If you go back to this figure, what is the vector which has component z component by x component must be minus tan psi. It is a vector perpendicular to this k vector and this angle is psi. Dz by dx is minus tan psi. This vector has a slope tan psi, this vector has a slope minus tan psi. So, dz by dx is minus tan psi and that is the direction of the d vector, and it is expected because d vector has to be perpendicular to the k vector. I need not have derived like this, but I know the d vector will always be perpendicular to k vector always. So, this is the d vector of this propagation direction, but also note that this equation tells me that Ez by Ex is equal to minus kx by kz tan psi. Now, if kx is not equal to kz, the electric vector z component by x component is not equal to tan psi, minus tan psi. So, the electric vector points in a different direction than the d vector. So, if kx is greater than kz, where should I draw the E vector? If kx is greater than kz, then it will be to the left or to the right of d vector. Ez by Ex will be bigger than dz by dx, right. So, E vector has to be here or here, between d vector and x vector, or on the other side. E vector has to be here, because its z component by x component will be more than the z component by x component of the d vector. This is if kx is greater than kz. If kx is less than kz, it will be on the other side. So, for this mode, for this propagation, the d vector and E vector are not parallel, and S vector now will be here. So, if I call this theta, this is also theta. So, please note that again for a propagation in the xz plane with k vector making an angle psi with the z axis, I have found two solutions. The first solution is a wave which is with this electric vector along the y direction, and S vector and k vector are parallel. The velocity of this wave is c by square root of ky, independent of psi. The second solution has its d vector perpendicular to k vector, and E and D are not parallel to each other. So, S and K are not parallel to each other, but the wave has a refractive index now which depends on the value of psi. So, as you change psi, the velocity of this wave will keep changing. If you propagate with psi is equal to 0, that means if you propagate along the z axis, then n will be square root of square root of kx. If you propagate with psi is equal to pi by 2, that means along the x direction n will be square root of kz. These are the same results we obtained in the special cases when you propagate along the principal axis direction, but in general if you propagate in the xz plane at some arbitrary direction psi, then this particular polarization state, this d vector direction which is perpendicular to this k vector direction, has its refractive index changing as you change the value of psi. And that is typical of anisotropic media, that please remember this solution has a psi dependent refractive index, the other solution has a refractive index which does not depend on psi. So, in anisotropic media again, for every propagation direction there will be two orthogonal linearly polarized waves which will propagate as modes of propagation. The refractive indices of these two modes will depend on kx, ky, kz and the angles of propagation. Now, in the course that we will discuss, we will be most of the time looking at uniaxial media. Please recall, uniaxial means kx is equal to ky is not equal to kz. Because of the symmetry between x and y directions, if you give me an arbitrary direction of propagation, I will always orient my x axis such that my propagation direction lies in the xz plane. Please remember, in uniaxial media x and y are symmetric completely because kx is equal to ky. So, if I choose my another axis in the xy plane which are oriented to the original x and y axis, there will be no change in dielectric constant tensor. So, if you give me a propagation direction, if this is my z axis, then I will choose my x axis such that the xz plane contains the propagation direction, and the problem that we have solved is the most general situation. So, in uniaxial media, because there is only one special direction z, kx and ky are equal, there is a kz. So, if you give me a uniaxial medium with these three principal axis directions, and if I propagate like this, and this is z axis, I will rotate my x axis so that my k vector, x axis and z axis lie in the same plane. Once I do that, the solutions are one electric vector along y, the corresponding refractive index given by this, the other electric vector along in the xz plane perpendicular, the d vector perpendicular to k vector, and the corresponding refractive index is given by this equation. So, I need to know only the angle psi with the z axis. Now, what is the refractive index seen by this wave when psi is equal to 0? Cos is 1, sin is 0, so I get n is equal to square root of kx. And what was the refractive index seen by the other wave? Square root of ky. And because kx is equal to ky, the two refractive indices are equal. So, if I propagate in a uniaxial medium along the z direction, the two eigenmodes have the same speed, have the same velocity, and this axis z direction is called the optic axis of the crystal, and there is only one such direction in uniaxial medium, and that is why it is called uniaxial. If you have kx not equal to ky, not equal to kz, one can show there are two directions in which the two eigenmodes will have the same speed, and so it is called biaxial. There are two axial optic axes in biaxial media. There is one optic axis in a uniaxial medium, and in a uniaxial medium by definition the z axis is the optic axis. An optic axis means if you propagate along the z direction, the two eigenmodes have the same speed. So, in next class what I will do is little more details, little more analysis or discussion of anisotropic media. We will discuss looking at the velocities of propagation and the polarization states. So, in the most nonlinear interactions we will see, we use the fact that you have now a medium in which you can tailor the refractive index by choosing an propagation direction. In isotropic media, you are only given one refractive index. Here, it is possible to choose a direction of propagation so that you can vary the refractive index depending on the direction of propagation, and this will become very helpful in nonlinear interactions. Okay, so do you have any questions?
Sir, in uniaxial medium, kx is equal to ky, kz is 0.
No. Okay, in uniaxial medium, please differentiate k and kappa. Kx is equal to ky is not equal to kz. All three are non-zero. The three diagonal elements of the dielectric constant tensor. Kx, ky, kz are the three diagonal elements of the dielectric constant tensor, and in the principal axis system, the matrix is diagonal. So, kappa x, kappa y, kappa z are the three unit vector components of the propagation direction. So, they are different. So, if you propagate along the z axis in a uniaxial medium, the two refractive indices, the two eigenpolarization states will have the same speed, same velocity. Yes?
Sir, what will happen to the intensity of the light?
What will happen to the intensity of light? Intensity of light does not change, because we are not looking at the absorption or reflection in the picture here. So, light will propagate as such. The polarization state will change, the two eigen components will remain the same, but the phase difference will keep changing with propagation. If the phase difference changes, that does not change the intensity, right. If I take a string and make it vibrate in multiple modes, and if there is no damping in the string, the total energy contained in the string remains constant with time. It is just the interference between the modes which is creating a change of shape of the string, there is nothing else.